Alrighty. Okay. So I think we were at where were we? Okay. So rewriting the code to use a signal handler. You now have all the code to make your program do something if someone hits Control C. So here's the code here. We have the sig handler die, which is the custom function that we want to run whenever we have a Control C signal, which corresponds to, I think, a SIGINT. Yep, SIGINT. We basically run this function called catch signal here that takes in the signal we want to register against and the function we want to register against. And notice how this function pointer here corresponds to the same type of function this void die shows, where we return void. We have the handler, so pointer to the handler, so pointer to die, and then the parameter list, which is one integer here. And this catch signal is just a helper function that will create that sig action struct, the one that's required to actually register the handler. We'll associate handler with the SA handler property, and then we'll also do sig ft set for setting the options, I think, and then flags, and we'll just throw it into sig action. So that's about it, really. Um, this program just asks for some user input. It looks like a name of 30 characters, so it's just gonna stay there until we actually enter something in. And I think we just are able to just hit Control C anytime we want. Um, yeah, so yeah, it says if we hit Control C, we want to print out goodbye cruel world, which is what happens here. All right. So, matching. Well, I could do this real quick. SIGINT. Well, the process was interrupted. SIG quit. I'm guessing. Whoa, this is harder. Never mind. SIG term. Someone asked the kernel to kill the process. So, okay, and then sig pipe. I'm guessing someone wrote, so the process wrote to a pipe that nothing's reading. Okay, so that, and then was it sig winch sig winch. I don't know, what is that? Sig watch something. How about sig FP? I know this one. Floating point error. Okay. Sig trap. Ooh, I know this one. Maybe sig winch is the debugger ask where the process is. Okay. Sig sev is probably like a segmentation fault, so illegal memory here. Sig term. Oh, we did that one already, right? Sig trap. Which one would that be? Probably someone asked the process to stop and dump the memory in a core dump file. I think the last one is sig quit. Okay, well, let's see. So sigid, the process interrupted, we got that one. Sig quit was someone asked the process to stop and dump the memory in a core dump file. Oh, okay. Sig FPE is floating point error. Sig trap, okay, the debugger asks where the process is. So sig winch is the terminal tree size. Sig sev is what we thought it was. Illegal memory. Sig pipe, okay, we thought the same. Okay, cool. So if the interrupt handler didn't call exit, would the program still have ended? No. So that's important to know. The die overrode the default behavior of what Control C would do. So Control C is usually like the pattern we use to kill a process. And basically, if you override the SIGINT interrupt signal, I guess, you will technically have to be responsible for calling exit. So I could write a program that completely ignores interrupts. You could, but it's not a good idea. In general, if your program receives an error signal, it's best to exit with an error, even if you run some of your own code first. So that's the hint right here. It's like you override the default behavior in this case. Okay. Use kill to send signals. If you've written some signal handling code, how do you test it? Fortunately, on Unix-style systems, there's a command called kill. It's called kill because normally it's used to kill off processes. But in fact, kill just sends a signal to a process. Okay, so caveat. Kill doesn't kill the process. Kill sends a signal. So one of those many signals that you can use, like a SIGINT, SIGTRAP, SIGWINCH, those types of signals can be sent by using the kill command. So I'm guessing it's going to be kill, and then the signal, and then the process name or ID. Yeah. So by default, the command sends a SIGTERM signal to the process, but you can use it to send any signal you like. And just for reminders, SIGTERM is going to be someone just asked the kernel to kill the process. Okay? To try it out, open two terminals. In one terminal, you can run your program. And in the second terminal, you can send signals to your program with the kill command. Okay, so kill, and then the signal you want to send, and then the process ID. Okay, so let's do this. Let's do less. Oops, less main.c. Oh, we're not. String test. Less main.c. Okay, and then let's open. Let's see. Control G or Control SC. Control BC. There we go. Another tmux thing. Okay, so we're in less right now. So we can do what is our process ID for that? Do we have btop? Oops, btop. Yeah, we do have btop. So if I did less here, we have PID of 100. Oops, 10794. So if I did basically kill dash int 10794, what happens? Nope, nothing happened. Was it? Less. Yeah, 10794. So int doesn't do anything. SIGINT. SIGINT in this case, we'll just say interrupted. So what happens if I do kill dash kill 10794? Oh, there we go. It killed. Okay, cool. So that one can't be ignored no matter what. Okay, sig kills, you can never override or kind of ignore sig kill. Each of the kill commands will send signals to the process and run whatever handler the process has configured. The exception is the sig kill signal. The sig kill signal can't be caught by code, and it can't be ignored. That means if you have a bug in your code and it is ignoring every single signal, you should always stop the process with kill-kill. So pro tip, kill-kill with the PID will always kill your program. And this is all done in command line. Okay, but you can actually programmatically send signals with raise, with the raise function. Sometimes you might want a process to send a signal to itself, which you can do with the raise command. Normally, the raise function is used inside your own custom signal handlers. It means your code can receive a signal for something minor and choose to raise it to a more serious signal. This is called signal escalation. Okay, more details here. So sending your code a wake-up call. The operating system sends signals to a process when something has happened that the process needs to know about. It might be that the user has tried to interrupt the process, or someone has tried to kill it, or even the process has tried to do something it shouldn't have, like trying to access a restricted piece of memory. But signals are not just used when things go wrong. Sometimes a process might actually want to generate its own signals. One example of that is the alarm signal SIG alarm, SIGALARM. The alarm signal is usually created by the process's interval timer. The interval timer is like an alarm clock. You set it for some time in the future, and in the meantime, your program can go and do something else. This makes the timer fire in 120 seconds. Okay, so this function alarm is going to, given some sort of integer here, which represents the seconds, when this number of seconds have elapsed, a SIG alarm signal will fire. And that actually triggers that to go to your process. And you can actually like listen for this SIG alarm interrupt and do something with it. And you can schedule that with the alarm command or the alarm function call. And yeah, so you do that, and then you just continue to do something else until 120 seconds occurs, and then you'll get a SIG alarm that gets fired, and you can have that custom function, whatever you register SIG AL RM with run. Okay, so when the timer expires, the timer fires a SIG alarm signal. When a process receives a signal, it stops doing everything else. So it's like super important. It'll cause your program to just stop doing everything else and handle the signal. Okay? But what does a process do with an alarm signal by default? It stops the process. It's really unlikely that you ever want the timer to kill your program for you. So most of the time you'll set the handler to do something else. And that's what I mean. Like if you don't if you do an alarm right here and you don't even have like a handler to handle the SIG alarm, it's just gonna kill your process by default, the SIG alarm thing. So you should probably always like register SIG alarm with some sort of handler if you're actually going to use alarm, because by default just kill. So alarm signals let you multitask. If you need to run a particular job every few seconds, or if you want to limit the amount of time you spend doing a job, then alarm signals are a great way of getting a program to interrupt itself. Okay? So, resetting and ignoring signals up close. Sure. You've seen how to set custom signal handlers, but what if you want to restore the default signal handler? Ooh, interesting. Fortunately, the signal.h header has a special symbol, sigdel, which means handle it in the default way, or sigdfl. There we go. So we can call our little helper function that registers uh, signal handlers, right, to a specific signal. So if we actually pass in sig dfl to sig term, it's actually going to restore sig term to the default handler. So there's also another symbol called sig ign that tells the process to completely ignore the signal. Okay, but you should be very careful before you choose to ignore a signal. Signals are an important way of controlling and stopping processes. If you ignore them, your program will be harder to stop. Okay, so if I receive a term signal, I should just exit like before. Control C, talk to the hand. I'm doing that. Okay. Can I set an alarm for less than a second? Yes, but it's a little more complicated. You need to use a different function called set timer. I think it's a precision problem, that's why. It lets you set the process's interval timer directly in either seconds or fractions of a second. How do I do that? Go to here for more details. Why is there only one timer for a process? The timers have to be managed by the operating system, so you can only call alarm, or you can only use one of those alarms in every process. The timers have to be managed by the operating system kernel, and if processes had lots of timers, the kernel would go slower and slower. To prevent this from happening, The operating system limits each process to only one timer. Okay, timers let me multitask. Great, so I can use them to do lots of things at once? No, remember, your process will always stop, whatever it's doing when it handles a signal. That means it is still doing only one thing at a time. You'll see later how you can really make your code do more than one thing at a time. What happens if I set one timer and what happens if I set one timer and it had already been set? Whenever you call the alarm function, you reset the timer. That means if you set the alarm for 10 seconds, then a moment later you set it for 10 minutes, the alarm won't fire until 10 minutes are up. The original 10-second timer will be lost. So yes, we can only have one timer at a time. So anytime you kind of call alarm again and again and again, it will just take the latest value and throw away the original. Okay. So this is a source code for a program that tests the user's math skills. It asks the user to work the answer to a simple multiplication problem and keeps track of how many answers he got right. The program will keep running forever unless the user presses Ctrl+C or the user takes more than 5 seconds to answer a question. When the program ends, it will display the final score and set its exit status to 0. Okay? Let's do it. Oh, this is long. Okay, it really says long exercise. See, how can we do this? Well, we can just kind of do it. We don't need to write it. Yeah, we do. It's a long exercise, so I think that's good enough to take a screenshot. Okay. And then we can be here. What? Did I mess something up? Let's see. Okay. Let's take a screenshot. Screenshot. Done. Okay. Great. That's where we want to be. Okay, and then let's do another one to the side. And that's the answer. So second one will be here. Okay, and we just blow this up. Control V, and let's hope this works. Okay. So let's read this again. So this is a source code for a program that tests the user's math skills. It asks the user to work the answer to a simple multiplication problem. It keeps track of how many answers he got right. The program will keep running forever unless the user presses Ctrl+C or the user takes more than 5 seconds to answer a question. When the program ends, it will display the final score and set the exit status to 0. Okay, so it'll display the final score and set the exit status to 0. So exit 0, I guess. So we can just do that. We can just write that. So this here will be exit 0. Okay, because it will just exit with a 0 status code. Time's up. What do we raise? Is this time's up? Okay, and then we catch the signal alarm to do what? Let's see. Probably raise. Okay, got it. So this is probably going to be the handler that So let's start back. Okay, so this is going to be the function that will end the game nicely. Should be final score. Yeah, it ends the game nicely. And this is the helper function that's going to register the handler against the signal. Okay, and we've seen this code before. And this one is going to be another handler that gets registered against another signal. And this one, I'm guessing, is the alarm one. So this one is going to be time's up. And this one, SIGINT, is going to be end game. Okay, and game. And the game is over whenever the time expires, or what else? What's the other condition? Control C. Oops. Yeah. Control C is the other one. So SIGINT is going to be the Control C one, which will directly end the game. Or we can just schedule it to eventually end the game automatically. So we do times up, and then we can also raise again, just kind of just forward that. I think it's just SIGINT like this because we want the same behavior. We want to display this. So basically, we can just raise a SIGINT. SIGINT will have that in game handler because it will get caught again. So we're forwarding it when the time is up for whatever seconds, 5 seconds, I believe. A SIG alarm is going to occur, which will then force this function to run, and then we'll put times up, and then we'll raise SIGINT, and we have endgame to be executed when SIGINT occurs, and it will run endgame here. Or if we Control C, we'll automatically raise that SIGINT event anyway, and then we'll run the endgame function. Okay, so what is this one? This is probably alarm 5 then. This stuff is just probably getting two numbers and just asking, what are your numbers or what are the answers? So two random numbers between 0 to 10. Okay, now you have 5 seconds. 5 seconds. It'll ask you what's first number times second number, and then you have to enter a number and check against whether or not that's the answer. Okay, cool, and you have to be fast. So, okay. So I think this is the answer. Let's see here. Okay. Exit 0, we got that. We also got SIGINT, times up, end game, and then finally alarm 5. Awesome. Cool. All right, test try. So to see the program works, you need to run it a couple of times. Test 1, hit Control C. The first time you'll answer the questions, and hit Control C. Control C sends the process an interrupt signal, SIGINT, that makes the program display the final score and then exit. Okay, so Control C to force it. Or you can just wait 5 seconds. The second time, instead of hitting Control C, wait for at least 5 seconds on one of the answers and see what happens. The alarm signal, SIG-ALRM, fires. The program was waiting for the user to enter an answer, but because he took so long, the timer signal was sent. The process immediately switches to the time's up handler function, and the handler displays time's up message and escalates the signal, so upgrades the signal to a SIGINT and causes the program to display the final score. Cool. Signals are a little complex, but incredibly useful. They allow your programs to end gracefully, and the interval timer can help you deal with the tasks that are taking too long. There are no dumb questions. Are signals always received in the same order they are sent? Not if they are sent very close together. The operating system might choose to reorder the signals if it thinks one is more important than the others. Is that always true? It depends on the platform. On most versions of Cygwin, for example, the signals will always be sent and received in the same order, but in general, you shouldn't rely on it. And if I send the same signal twice, will it be received twice by the process? Again, it depends. On Linux and the Mac, if the same signal is repeated very quickly, the kernel might choose to only send the signal once to the process. On Cygwin, it will always send both signals. But again, you should not assume that just because you sent the same signal twice, it will be received twice. Okay? The fact that you just have to know that the signal will come. So the operating system talks to the process using signals. Yep, the programs are normally stopped using signals. When a process receives a signal, it runs a handler. For most error signals, the default handler stops the program. Handlers can be replaced with the signal function, and you can send signals to yourself with RAIDs. The interval timer sends a signal alarm signal, and the alarm function sets the interval timer. So alarm function will trigger the signal alarm signal. There's only one timer per process, and don't use sleep and alarm at the same time. Kill sends signals to a process. Kill-kill will always kill a process. Safety mechanism. All right. Cool. Gonna get to the most fun part of the book. Still have some time, so we could just start reading it, and then next time we'll take our time and digest this. This is gonna be a long one, a long, fun one. Networking, sockets, and networking. There's no place like 127.0.0.1 or home or localhost. Servers are us. How can I help you? A new client, darling? I always knew your blabbing would come useful one day. What the? That doesn't make sense. Anyway, programs on different machines need to talk. Oh, okay. Oh, I think I know why. Okay, I think we're gonna create something that does this. Okay. Programs on different machines need to talk to each other. You've learned how to use I/O to communicate with files and how processes on the same machine can communicate with each other. Now you're going to reach out to the rest of the world and learn how to write C programs that can talk to other programs across the network and across the world. By the end of this chapter, you'll be able to create programs that behave as servers and programs that behave as clients. Okay. So we're going to create one program that is like a C client that connects to another program that we write in C that is a server. The Internet Knock Knock server. Okay. C is used to write most of the low-level networking code on the internet. Most network applications need two separate programs, a server and a client. You're going to build a server in C that tells jokes over the internet. You'll be able to start the server in one machine like this, okay? Internet Knock Knock protocol server, I guess? Other than telling you it's running, the server won't display anything else on the screen. However, if you open the second console, you'll be able to connect to the server using a client program called Telnet. Telnet takes two parameters, the address of the server and the port of the server it's running on. If you are running Telnet on the same machine as the server, you can use 127.0.0.1 for the address. Cool, and this is and a port. You need to specify a port. Okay, so a warning is that we'll be using Telnet quite a lot in this chapter to test our server code. Do we have Telnet? Okay, we have Telnet. Is it quick? Yeah. Okay, so basically connect, then you just interact client-server model with our program. So you will need Telnet. You will need a Telnet program in order to connect to a server. Most systems come with the Telnet already installed. You can check you have Telnet by typing this. So on Linux, I think you just need to do sudo apt install telnet, and I think it will just work. Yeah, it's already on apt, so you can just install telnet that way if you don't have it. Alright, I'm gonna just stop it right here and continue next time. I'm actually a little tired from work, so thank you.